Okay. All right. So welcome everyone to the new member lecture for aerodynamics. I'm Aerodynamic, and let me just get this started. There we go. Shoot. Do you know how to like just do one side at a time? Because I think it's projecting the wrong screen. Oh. Because that screen should be the one that's being projected. All right, sorry about that. There we go. All right, welcome everyone. I'm Aerodynamic. I'll be your presenter. I'm the aerodynamic system lead, and just wanted to give you guys a quick lecture to kind of go over kind of like Aero in a nutshell. So starting out, let me just give you a quick agenda. So I'm just going to give you a generic overview of why exactly we have Aero in the car, why Aero matters in the first place, kind of go from there, describing some of like the forces that drive our design and also how we actually manufacture our package. So I'll start by giving you guys just kind of like a brief little overview and kind of like a review of what aerodynamics actually is and what it means. So when we say aerodynamics, what aerodynamics actually is it's really just the study of how air interacts with solid bodies. It could be a car, it could be a block, it could be a potato. Generally, it's just the study of how air like interacts with something that is solid and not gaseous. As you can see from this animation, lots of complicated interactions can occur, but in general, they're all governed by very fundamental physical principles. So the first equation up there is just Newton's second law. We say that if we have some kind of mass that's accelerating or moving, that quantity is called a force. And the second equation is essentially the second law of thermodynamics, which states that the change in energy of a system must be equal to zero. And you might be asking yourself, well, that might not make sense. I mean, I can push on this thing, I can move this piece of eraser. But the thing is, those forces are always balanced by things like friction and things like work. So in general, for any kind of system, it could be a car in a wind tunnel, it could be me moving forward through this room, it could be anything. The change in energy has to be equal to zero. And specifically how that's balanced is by the change in kinetic energy, potential energy, and internal energy. We don't really care too much about internal energy, that's kind of like chemistry stuff. But I just want you to bear that in mind going forward. So the third equation is the equation of momentum. You'll hear me say that word a lot because it's very important to how we study structures in Aero. All momentum really is it's kind of like the integral of force with respect to time. So you'll see momentum is essentially your mass times your velocity for some kind of fluid or object. And we can define our force as a change in our momentum over time. Or more specifically, we can describe it as a mass times our change in velocity over time. That's important going forward because the way we describe our kinetic energy of a fluid, a body, anything is by a mass multiplied by a velocity squared. So if we change our velocity somehow, or more specifically, we change our momentum, then we end up changing our kinetic energy. So if we increase our momentum, then we end up increasing our kinetic energy of our fluid. Consequently, our potential energy needs to change due to the second equation because that condition always needs to be met. The kinetic energy and potential energy need to cancel out. So all of this is to say, when we have kinetic energy and we end up increasing it by changing our momentum, and that momentum change comes from the interaction with some kind of a solid body, we end up changing the momentum of the fluid. And balance is essentially that we end up being pressure whenever we change our velocity. So that's kind of Aero in a general nutshell. That's about the most easy to understand way I could write it. But basically, if we change our velocity, we have to balance that out by changing our pressure. So going forward, we know what Aero is, but why does all that matter? Why have a wing on a car? Why have any of that? Well, the answer is aerodynamics affects the vehicle's performance. Again, drag typically makes it harder to accelerate because it directly opposes the motion of our car. So you might be thinking, oh, well, drag is bad. Our car can't really go fast if it's got drag on it. So why have it in the first place? The answer is because we want downforce. So downforce generally improves our ability to corner with our vehicle. Specifically, it does that by increasing the amount of lateral force on our wheel required to increase its slip angle. Now you'll see the figure in the bottom left side of the screen essentially shows what that slip angle is. When your wheel is moving forwards, i.e. just in a straight line, it's not actually moving forwards. There's always, your wheels are always kind of slipping and sliding all over the place and moving at a different velocity than what you might think based on just the way the wheel is oriented. And where Aero comes into play is we increase the normal loading on our tires, which in turn changes the slip angle of our tires. So that's the main reason why we want Aero and specifically wings on our car, is because you can see with an increasing vertical load, we decrease our package's sensitivity to the lateral force with respect to its slip angle. If this all sounds kind of complicated, don't worry, it's really not. It's just kind of like a lot of stuff that you gotta get acclimated to. So that's kind of like a general overview of what we do on Aero. So let me get into kind of break down and show you like what all the aerodynamic forces are and kind of like a high level understanding. So all our aerodynamic forces are is a difference in pressure between a top surface and a bottom surface. So the way we generate downforce is we make our wings with airfoils, and airfoils are specifically shaped to create a pressure difference between the top and bottom surfaces. Typically, a high pressure fluid will want to move to a low pressure region. So you end up getting some kind of suction when you have a fluid that's high pressure. So for example, the figure on the left is showing a pressure sweep of our rear wing. You can see the high pressure region tends to bleed into the low pressure region. Now, when that happens, what you're doing is fundamentally you're changing the momentum of your fluid with the shape of your airfoil. And what that does is, as we've established before, that's what generates a force. You can also see over here, there's a velocity difference too. So if your pressure is really, really high over here, you can see the velocity tends to decrease. Whereas if your pressure is really, really low, the velocity of the air increases. So there's kind of like a balancing act between those two. That's fundamentally all we do in order to generate lift and drag. And you can also see these equations up here are essentially the equations of downforce and drag. And we see that the downforce of our package and our drag is proportional to the velocity squared of our car, which this represents our airspeed, but also we assume that our airspeed is about analogous to our car's velocity. So the car's going forward 35 miles per hour, the air is going back 35 miles per hour, if that makes sense. And then the only dependencies are really just this V infinity squared and the CL and CD. Those are basically just measurements of how well our shape of our airfoil can generate lift or drag, depending on which equation you're looking at. Make sense? Okay. If you guys have taken intro to Aero, then you've kind of like been introduced to these concepts already. I'm just kind of going over them just to kind of give us all a level playing field going forward. So aerodynamic forces, really cool. They're the main things that we look to develop with our wings, and specifically we want to make downforce. Now, You'll notice there's only really one way we can make downforce. Well, that's not entirely true, but in general, the way we make downforce is we have a pressure difference between the top surface and the bottom surface of something. And that generates a force which points in the net down direction. Now, that might be the case for downforce, but it turns out on the other end of the spectrum, there's a lot of ways we can generate drag that aren't specific to just pressure differences. We can have skin friction, which kind of is shown in the bottom left figure. The bottom left figure is actually the white grayish sections are little particles of smoke that are inserted into a wind tunnel test, and the bottom boundary represents some surface. You can see as you get closer and closer to some solid boundary, your fluid tends to get slowed down. Now, that's how we develop drag, is by having air particles that are essentially stuck to whatever body we're designing. So that's typically pretty bad for our aerodynamics. You can't really avoid having a boundary layer. Everything has a boundary layer if it's moving through a fluid, because air just kind of tends to get stuck on things. Like in this room, you probably have a very small boundary layer around you of air. But what we can do is we can try to keep that boundary layer attached to our profile as we can, because that tends to induce less drag than if our profile was, for example, very turbulent. There's also other kinds of induced drag, such as the drag from generating lift. So when we have a lifting surface like a wing, we tend to have mixing of our flow relative to our end plates, because again, we have high pressure flow in here, probably low pressure flow in here. So I'm going to play this animation, and I want you to pay particular attention to these sections of the airflow. You'll see, I can play this. So you can see as you move along the wing itself, you'll notice this region tends to form a very strong vortex. It turns out that this ends up inducing a lot of drag just simply because of how the momentum change, the change in momentum occurs. You can see we have a very low velocity, high pressure region here that ends up wanting to mix with this low pressure and this low ambient pressure out here. And that generates very strong vortices near the edge of our end plates, which is bad. That's something we want to try and avoid and mitigate if possible. So yeah, that's about it in terms of kind of setting up like our forces. But specifically, the balance of our forces is very important. We could design a big front wing, a big rear wing. It doesn't matter if it's not stabilizing our vehicle in the way we want. And the criteria we typically have for ourselves is we want our center of pressure, which is the point through which the aerodynamic forces tend to act, to be really of our center of gravity and at about 56%. So the reason why is because our center of pressure's position essentially determines how our vehicle turns. When you think about it, if I have my center of pressure further forward here, then I end up pushing more on these tires than these tires, just because the loads have to travel less distance to get here. So they'll naturally tend to develop more loading on these tires. When that happens, your front tires will tend to have less of a slip angle than your rear tires. So what happens is you might be able to take a corner when you're turning, but because your rear tires have less grip, they might slip out before your front tires do. And if that's the case, then you tend to spin out on track into the corner, and that's very bad. It's difficult to correct yourself from this position. It's it generally makes steering more difficult because your steering inputs, your vehicle's response to your inputs is more sensitive. So you can turn your steering column at less of an angle and turn at more of an angle than you would if you had a rearward center pressure. So front center pressure, by the way, is what's referred to as oversteer. On the other end of the spectrum, if we have understeer, you'll notice in this case, if the car has a rearward center pressure, it will tend to take more than input from our driver to turn it, and it won't tend to corner as well. But the benefit of this is that So not only does, so most of the safety features of our car are more towards the nose of the car, like the IA and all of that. That helps to prevent our driver in the case of a collision. Not only that, but in this case, all you really have to do to get yourself back on track if you start understeering is just stop the car and then go at a slightly slower speed. And obviously, we're all novice drivers. We're not professionals yet. So that's very advantageous because in the case of testing, we can, and even on track at competition, we can very easily correct ourselves and understeer. Whereas in an oversteer, if you're going to a really bad oversteer position, basically that's just less of an issue to deal with than, that's more of an issue to deal with than an understeer position. Does that make sense? Okay, so that's one of the main things that we're concerned with is just making sure that the balance between the front wing and the rear wing is where we want it to be, which is rearward of the center of gravity of our car. So there's other stuff to consider too. So for example, aerodynamics is really funky. There's a lot of really cool stuff. So for example, there's this physical concept known as ground effect. So what that is essentially if you have some kind of a wing that is in close proximity to the ground, it works out that it essentially has no boundary layer because of how close it is to the ground. And that increases the efficiency of your device. You can tend to more easily produce lift or downforce if you're in close proximity to the ground. So, for example, the front wing is very efficient because of this, because we need less wing surface area to make the same amount of lift, because it's in ground effect, because it's very close to the ground. This is all due to the Venturi effect. Essentially, what you'll find is if you have a constriction, so if, say, for example, you have like a big length of pipe that has a massive diameter, and you shrink it, well, to get the same amount of mass or energy through it in the same amount of time, you need to accelerate your fluid. So the air ends up getting pushed under here at a high speed. High speed equals low velocity. So you essentially generate a massive low pressure region under this thing, and then the high pressure of the car tends to suck down on the car quite dramatically. So that's kind of like a basic overview of ground effects. So now we want to get more into what you can kind of expect for design on the aerodynamic system. So obviously, when you think aero, you think wings. You think big boring wings, big Cessna wings, that kind of stuff. So in general for wings, we utilize 3 different kinds of devices. We have a front wing, a rear wing, and our undertray. Undertray is, it's kind of weird to call it a wing, but it's a device that makes downforce, so it's close enough. And the cool thing about our Aero package is, as we said before, the downforce that you generate is proportional to your velocity squared. So if you drive the car fast enough, you could technically drive it upside down. And even if it doesn't make like physical sense, it makes mathematical sense. So it's pretty cool. I think the current package is making about 600 pounds of downforce at about 50 to 60 miles per hour. So you technically could do it. So more specifically, so the front wing. It's the first thing you see when you look at the car, other than the rear wing and the monocoque. It's the first point of contact between the car and the air. So you can essentially assume that all the air in front of the car is pretty laminar. It's behaving pretty well. That all changes once you hit the front wing because it's the first solid body that it interacts with, and it kind of loses momentum from there. You can see on the right, there's a lot of fancy flow conditioning that you can do with the front wing. This is an example of like a professional Formula One wing. You can see they're doing a lot of things with the air with their front wing. So you see a vortice here that's being generated. That's specifically to pull the wake of these tires outward from the car because that ends up inducing less drag. They're also doing something similar over here to kind of manage the wake of the tires. The tires tend to kick up a lot of turbulent air because they essentially act as like a mini compressor. You think about the air, if the air is like flowing towards the tire, it sees the tire spinning and it basically gets like caught up in it and shot out. And additionally, the front wing operates in ground effect, so it is very aerodynamically efficient. what we see is because of this, it tends to oversteer more at higher speeds, simply because it begins making more and more downforce. Again, downforce is proportional to the velocity squared. So as you go faster, you tend to generate more downforce. That's about it for the front wing. And naturally, the front wing is balanced out by our rear wing. The rear wing is a big honking boy. It has about 5 wing elements right now, as well as large end plates. The reason for this is because it provides basically all of our rear downforce. If you think about it, for the forces to balance rearward, we need more rearward lift. So basically, our main concern in designing our rear wing is obviously to try and keep the drag as minimal as possible, but it's also to try and keep our balance of forces more rearward. So usually when we design our rear wing, we're more concerned with getting our center of pressure where it needs to be and generating more downforce than the drag that's induced on it. Yeah, you can kind of see in that image the cascades. So this is kind of terminology, but these wings that kind of come off of the main element are referred to as cascades. What you see is essentially they help generate one large high pressure region that acts as essentially one large airfoil profile. So that kind of tends to generate a lot of downforce, but you can kind of tell if you look at it in terms of like where the resultant forces from all of these wings is going to be. They do end up generating more drag than if you were to try and orient them in a different way. But again, with the rear wing, we're primarily concerned with making sure our car is having the appropriate load balance and that it's understeering. So move forward. And finally, in terms of wings, we have our undertray. So the undertray has a ground clearance of about 1 to 1.5 inches. So it is in very, very close proximity to the ground, and it is definitely a ground effect device. As a result, it is very efficient at producing downforce. And you might look at this thing and say, oh, where's the wing? There's no wing. Well, that's because this thing operates purely off of the Venturi effect. So you'll notice that there are these little cutouts right here. These are essentially diffusers that act to kind of funnel air out from the underbody of the car in a very smooth and even manner. The reason for that is if you look at the pressure map, you can see there's a very low pressure region in here. And that's what typically generates a lot of the suction, because if you think about it, we can kind of see it in the scene right here. This is an animation that I'll play in a few seconds. We typically have a much lower velocity up here than under here. The air is being essentially constricted, so the cross-sectional area it has to flow with is being decreased, so the velocity increases. And the result of this is we have a massive suction on the undertray just because of how low the pressure gets and how fast the air is being shot through it. But we need to discharge the air, otherwise it stagnates, which isn't good for generating downforce. So real quickly, I'll just play this animation. So you can see this is a cross-sectional view of our undertray. You can see this is our velocity that it's showing right now. You can see as we move across the surface of it, and this is kind of like a sweep view, the velocity starts out very, very high, so very low pressure here. You'll see the rest of the body of the car has a very, very low pressure. So in terms of downforce, you actually end up generating a lot of downforce just purely from the exchange of momentum that happens when these two flows mix with each other. You want to make sure they mix evenly, because then you get stagnation, you get a really bad rake, and that's not really good for drag. And as you can probably tell, it's a big project to put this thing together. It has about 11 separate diffusers that all diffuse air. So moving on. Some other stuff we designed, we have an active aerodynamic system. I'm sorry, this is kind of an old photo of the rear wing, but essentially we have an active aerodynamic system that we design every year and try and implement that is intended to actuate our rear wing. So if I go back a few slides, actually, you can see on here there's a very high pressure region here. And that tends to generate a high downforce. But that might not necessarily be what we want if we're going through a straightaway, because in a straightaway, we want to accelerate as fast as possible. And like we said earlier, drag gives us our ability to accelerate. So we ideally want to be able to actuate these elements so that way we're making less drag on our rear wing, which is the biggest producer of drag on the car, when we're going through a straightaway. So basically, we implement this system because it helps us have less drag on our car, and less drags makes it easier to accelerate, and so the car goes fast. Yeah. Additionally, so that's kind of it for our kind of traditional design. So when you think Aero, you think, oh, wings, downforce, lift, all that stuff. But really, aerodynamics is a tool that can be applied to solving a lot of different problems. And as it turns out, our system is best equipped to analyze these problems involving airflow. As such, we help design the radiator duct to funnel air through the radiator core to kind of help try and cool down the engine. We've also been helping the brake system kind of investigate designing ducts to cool the brake rotors. And we're also trying to help create ducting to help cool the ECU for electrical. Basically, if there's a problem that can be solved with aerodynamics and we have the time to work on it, then we can solve it. But then the question becomes, how do we analyze these problems? How did I get all those fancy little animations and sweet views and all of that? The answer is we use this little program called CFD, Computational Fluid Dynamics. So what CFD is essentially, it's a pocket wind tunnel that we can use to perform rapid iterations of our aerodynamics but at kind of a higher level, what it is it's a program that's designed to solve the Navier-Stokes equations and different flow field equations to hold the change in momentum that the presence of our car exerts on a flow field. That sounds complicated, it's because it is. This is about the most complicated part of Aero, and it's something that we're always learning more about. Like, this is kind of the crux of our analysis, apart from testing and all that. But yeah, so what this thing does is it solves these equations. These are the Navier-Stokes equations. If you've ever heard of them, you probably know they're one of the millennium problems. They are technically unsolvable analytically. So what CFD does is it essentially applies a bunch of approximations to solve this, because I don't know about the rest of you, but I don't want to solve this. It looks like a lot of work. It looks like it would make my brain explode or something like that. So instead, what we do is we use our computer. And what is our computer good at doing? It's good at working with zeros and ones and solving very simple problems. So we want to try and simplify our problem as much as possible. And obviously, if you take like a full car and you throw it in here, it's not going to know what to do at first. It's going to look at that and it's going to be like, okay, I've got this weird curve here. The air is going to interact with that somehow. I don't know what to do. So instead, what we do is we break our problem up of air flowing through a wind tunnel over a car into a bunch of little problems. So instead of, say, flowing around the entire car, why don't we just look at air flowing in this part? And then if we know what the flow is like there, then we can kind of approximate what it'll be like there, and there, and there, and there, and there. And that's what CFD is. So basically, CFD takes a problem that is infinitely complex, and it breaks it up into a finite number of less complex problems. So each and every single individual node and each and every single individual cell, it is running through and solving an approximated version of these Navier-Stokes equations. Obviously, it's an approximation. It's not an exact answer to the problem that we're feeding it. But it gives us a decent approximation of how our package is performing and how the car is performing aerodynamically, which is why we use it. And you can also make neat little animations to show to people that don't know much about aerodynamics. So that's an added benefit. But yeah, so CFD, our main analysis tool. There's a lot of developments to be made. There's a lot of stuff we can do with it. We kind of operate with it at a very basic level. But as aerodynamicists, it could be your job to help us develop our methodologies, our meshing, and everything like that going forward, because that's still something that we're learning over time. All right, so this is the final section, manufacturing. So let's say we've designed a package, we've analyzed it, we've iterated it, we're confident that we're where we need to be in terms of making it, and that it'll do good if we make it. But making it's the hard part. So in terms of manufacturing, it turns out making the wing entirely out of solid aluminum, pretty expensive, pretty heavy, not really doable. So what we do instead is we manufacture with composites, because specifically you can make parts that have a very high strength to weight ratio. What that basically means is you have a part that is less dense than something similar, but it has a similar strength. So composite parts are kind of like a cake. That's kind of a weird statement, but it's true. When you have a cake, you take flour, egg, sugar, whatever other ingredients, and you add them together, mix them together, bake it, and you get a cake. With composites, you take carbon fiber or some other fabric, you impregnate it with an epoxy resin, and then vacuum bag it around a mold. And suddenly, the properties of the carbon fiber, the properties of the epoxy mix together to give you something entirely new. And it's entirely, the strength of our part is entirely process dependent, which is something that's cool about composites. It's also something that's a little difficult to understand and model. But our typical composite process involves choosing some kind of lamina or fabric. So for example, carbon fiber was used for all the wings because it has a high strength to weight ratio. It also looks really cool. And then we mix it with resin and hardener in order to kind of begin curing our laminate. We combine them together, and then we apply some kind of film medium and breather. That's what in this image, this is actually an image of when we were bagging our Undertray molds last year. You can see there's this white stuff in here. That's actually just cotton fabric, because cotton fabric helps us to give a medium for air to be sucked out of our vacuum bag when we go to vacuum our parts, because the act of having a vacuum that sucks our parts onto our molds is ideal because it gives a very nice surface finish on them. So that's kind of the general process, I guess, for manufacturing composite parts. You start with some fabric, put epoxy on it, apply it to a mold so that it cures into a specific shape that you want, and then vacuum it so it has a good surface finish, and then you're pretty much done. Yeah, like I said, cake. So specifically, some of the techniques we use is we make wing sandwiches, which is where we essentially cut out of foam a male mold and a female mold for our wing profiles. We do that using a CNC hot wire because it's able to very easily cut through the foam like a hot knife and give us a very nice surface finish on our for our airfoil profile. Then on top of that, we stack 2 layers carbon fiber, typically 2. It really depends on if it's like a structural part or not. More plies typically makes it a bit stiffer, which can be nice. But typically for the wings, we only use 2 plies because it gives us a good surface finish as well as the properties that we need structurally. And then we have Maya, which is kind of like a plastic finishing agent. That's actually how we got this rear wing to look so glossy. Yeah, and then once all that's together, we vacuum bag it. We also tend to make body panels for the car as needed. We essentially make the molds for that typically out of sheet metal because it gives us a nice surface finish on our parts and it's easy to release from using conventional mold releasing agents. Yeah. So that's kind of like a rundown of our whole cycle. So we begin by designing our car. We design the wings of the car, any bodywork that needs to be made, and we go from there and now analyzing it in CFD, and then we make it. And that's kind of it in terms of Aero. Obviously, there's more nuance to it. All of the individual parts of Working with it involves a lot of care, a lot of process and precision. And if that interests you, then this is definitely the system for you. So that's it for me. If you guys have any questions, I'll open it up to you. But other than that, thank you for attending. And yeah. So, yes.
So what parts would you use Kevlar instead of carbon fiber for?
Okay, so that's a good question. So, what's your name, Barry?
Jacob.
Jacob. All right. So Jacob asked, what specific parts do we use Kevlar for? So that's a good question. We typically use it to line the bottom of the undertray because Kevlar is more abrasive resistant than carbon fiber. We also make the heat shields for the frame that protect the driver from the heat that's radiated off of the exhaust out of it, because it has very good thermal properties. It doesn't really tend to heat up as much as like carbon fiber does. So that was a good question. Any others? Yes, what's your name?
Is the Aero package changing from F21 to F22, or is it kind of be the same?
Okay, so the Aero package is so there are a couple of changes. The undertray geometry has changed slightly. So last year our major addition was like double diffusers to it, and just bringing it back in the first place. It was actually our first time running an undertray in about 3 or 4 years. But so to break it down from front wing to undertray to rear wing, front wing, the main change has been adding a sweep to the wings. That was done because it helped us tune our center of pressure. It decreased the drag on the wing, and it also seems like it might have some desirable properties for stabilizing the car as it's cornering. For the undertray, the inlet geometry is changing to help kind of funnel more air through it and discharge it, which has increased our downforce. For the rear wing, the main addition, and I'll just go back to the rear wing slides. So the main addition is these two tandem wings right here. You can see them up there. That was done because we found our center of pressure wasn't really where we wanted it to be last year. So we added these wings because, as you can kind of see, this is kind of showing where all the individual streamlines of flow are flowing across the body. If you look at the tandem wings relative to like the cascades, they've actually got very well attached flow. That's good because not only does it mean we have more area to generate downforce, but this system actually doesn't make as much drag as, for example, this cascade does. So those changes have kind of occurred already, but it's a good question. Anyone else? Yes.
The sweeps on the front wing.
So the sweeps on the front wing? I don't think I did any for the front wing. Were you talking about one in particular? Or?
Well, because you mentioned that you were like adding them, I think.
Oh, you mean like the actual sweep to the front wing? Yeah. So if you look in this picture, last year's wing was essentially a rectangular profile. So you can see there's kind of like an angle here. So that's what we refer to as sweep in a wing. So if you have an ordinary like rectangular profile, say like this, you expect it from like a top-down perspective to look something like this, whereas a swept wing has more profile that's like this. And that changes a few things about the wing's performance. To kind of condense it into just a few sentences, basically this makes it to where when our car is turning, it tends to stabilize the car a little better than it would otherwise. It also does decrease the downforce of it slightly, but that was done to kind of balance the center of pressure and bring it to where we wanted it to be.
Which is where?
About 56% rearward. Granted, that's based on some old data, and that's something that we're currently trying to ascertain, but that's kind of where we're trying to put it for now. Also, additionally, so adding this taper kind of ended up mitigating the effect that the ground effect had on the wing. So what I mean is the center of pressure tends to migrate as the car increases its velocity. So car goes faster and faster and faster, the center of pressure moves forward and forward and forward. This configuration ended up kind of decreasing the migration of it. So if it started at 50, so last year's package started at a center pressure of about 54%. at 54% rearward at 35 miles per hour, and it shifted forward to around 52% rearward and at around 80-ish miles per hour. But with this package, it goes from about 56 to 55.5. So it's a much narrower, it's more concentrated, if that makes sense. Any other questions? This is open to people in Zoom as well. All right. Well, if not, thank you all for coming, and I guess I'll see you around at the shop.